Starting with Part A, software engineering is fundamental different from simple programming. It applies rigorous engineering disciplines to build reliable maintenance software. For a highly stable, scientifically accurate applications like ImageJ, the waterfall SDLC model is highly appropriate. It relies on strict phases gates, meaning we must completely establish and model our requirements and architectural designs before a single line of code is written. This prevents costly logical errors during development. To understand our domain, ImageJ is built specifically to process complex scientific image datasets. In software engineering, we categorize its traits into functional and non-functional requirements. Functional requirements are the explicit actions that a system must perform, such as applying filters or calculating values. Non-functional requirements, on the other hand, define the system operational quality, such as its calculation precision, security, processing speeds, and execution reliability under heavy data loads. Here I have defined 4 specific functional requirements and 2 critical non-functional requirements for ImageJ's particle analysis. From an SE perspective, NFR1 performance efficiency is critical to ensure that scientists does not experience processing bottlenecks when dealing with huge image matrices. More importantly, NFR2 accuracy and precision is completely non-negotiable. Under the SE principle of reliability, if the software introduces rounding errors into the geometric calculations, it directly corrupts the scientific data, rendering the academic research invalid. Let us look deeply into system requirements matrix. In professional software engineering, a common failure point is treating requirements as a simple checklist. For a scientist platform like ImageJ, we must analyze the direct operational dependencies between functional capabilities and non-functional quality attributes. For example, under functional requirements 2 and 3, the user relies on the system to transform grayscale pixels into a binary mask and filter them based on geometric criteria like size and circularity. This capability is completely dependent on our 2 non-functional requirements. Let's look at NFR1 performance efficiency. Why is a strict 3-second runtime threshold necessary? Because in a live laboratory environment, researchers process massive multi-gigabyte image arrays. If the underlying algorithm scaled poorly, it creates a severe processing bottleneck, resulting in application freezing or system-level memory thrashing. Even more critical is NFR2, metric integrity. Under the software engineering principles of system reliability, our geometric calculus equations must achieve absolute 100% precision with zero mathematical rounding errors. In a standard commercial applications, a minor rounding difference might be acceptable, but in scientific computing, a single pixel miscalculations alters the parameter data, corrupting the experimental datasets and completely invalidating the academic research findings. Therefore, NFR2 is our primary. Moving into system deconstruction, ImageJ heavily relies on a centralized repository architecture pattern. This choice is highly logical because it allows hundreds of independent user-built plugins to manipulate the same core pixel matrix data in memory without creating duplicate files, which would otherwise crash system memory. To verify this architecture, we implement 2 testing strategies. Unit testing using JUnit to ensure individual geometric mathematical methods work perfectly in isolations, and system integrations testing to verify that data pass seamlessly from the image loader to the final result display without memory leaks. Now, looking at part C, this is the use case diagram modeling the system boundaries. The system boundary box clearly separates the core software features from external entities. Our primary actor is the scientific researcher. Notice the structural relationship between UC004, which is particle analysis, and UC002, threshold adjustment. There is a strict include dependency pointing to UC002. This models the system constraint that the particle analysis engines cannot execute unless a binary mask has been successfully generated first. To ensure a deep understanding of our core feature, this table specifies the precise behavioral flow of UC004. The precondition mandates and activate calibrated binary matrix. The main flow covers the step-by-step interaction between the researcher typing parameters and the algorithm scanning the coordinates rows. Crucially, to satisfy robust software design, I have defined exceptional flows. If a user types invalid, non-numerical text, or if the filters is too tight and isolates zero objects, the system handles these exceptions gracefully through safe alternate path rather than crashing. To visualize the exact chronological executions of this use case, I developed this vertical activity diagram using standard UML notations. The process flows strictly top to bottom, starting at initial nodes. There are two critical decisions nodes acting as quality control gates. The first diamond checks if the user's boundary inputs are valid. If not, it loops back to the dialog box, creating a safety validation loop. The second diamond checks if any objects were actually found, deciding whether to route to an exceptions message or build the live result layout before finishing cleanly at the final bullseye node. To provide concrete empirical proof that my behavioral modeling perfectly matches the real-world system runtime executions, here is the first verification screenshot. This captures the input phase of UC004. You can see the active parameter dialog window successfully rendering on top of the binary bloops sample canvas. It demonstrates the exact moment the system pauses at the validation stage, waiting for the researcher to input values and click OK. Finally, this second screenshot proves the successful executions and fulfillment of the system post conditions. Upon clicking OK, the algorithm dynamically executes the matrix scan. As verified on screen, the system instantiates 3 coordinates output, the outline window displaying 64 numbered object traces, the result table calculating precise geometric matrix for each individual trace, and a summary report confirming the statistical throughput. This directly correlates with the final success path model in my activity diagram. To conclude, this part highlights the academic and industry foundations of this project. Every requirement matrix, architectural choice, and UML model presented was cross-referenced with established engineering benchmark. We adapted Iron Survival's software engineering frameworks for our SDLC structure and analyzed the office image decor ecosystem documentations to deconstruct the centralized repository pattern. Additionally, our use case and activity diagrams strictly follow standard UML notations guidelines provided by Visual Paradigm. These research foundations ensures our system analysis is both practically viable and academically right. Thank you for your time, and that's all from me. Bye!